All right. Thanks everybody for coming out. We're going to start next talk here. What I'm talking about is the entropy of obfuscated code. All right. So what I'm actually looking at is using, so real short story, using math to detect the kinds of attacks we discussed in the, well, previous talk, right? So the kinds of code that get hidden in a document, the kind of code you see embedded in documents that gets randomized, like the stuff coming out of Metasploit, like the stuff coming out of Unicorn that we saw in the last talk, right? So let me see if work. There we go. All right. My name is Adam Hogan. I'm a security engineer with Cisco's Advanced Threat Group, which means I came over from the SourceFire team, and it means, first and foremost, I can't help you with your router or firewall. I'm focused entirely on the malware. If you want to talk about that, great. Hit me up. So a quick outline, what we do is look at some of the malware that's embedded in documents, the kinds of attacks we're seeing, like, hey, open this document, and we launch malware that way. Talk about how to extract that code from malware so we can take a closer look at it. And then we're going to go into just a bit of information theory so we can try and catch very common ways in which these attacks are hidden from traditional detection schemes like IPS or AV. And we'll do that by measuring entropy. I'll go over what that means and how we can do it. There's a little bit of math involved, but frankly, there's a lot of libraries available. If you've ever done Python before, you can be using these techniques to catch malware in a few minutes. Okay? And they'll actually go and pull data from malware. I'm going to go through a few hundred samples of malware, pull out the statistics, and actually show you that we can do detection on this, and that there are statistical differences between the sort of malicious code we see people randomizing and normal code. So we actually have a way to automatically detect this stuff and process a lot of this data in mass. And of course, I will show you some outliers, because now that I've quantified this data, I'm actually able to find that there are some outliers to it already, and that's sort of part of the fun of being on a blue team. Means that when you find a new way to detect malware, it's usually a matter of time before bad guys find a way around it, and that's already happening. I'll show you what that looks like. Okay, so document malware, I mean the sort of code that gets hidden in Office documents, right, where you see VBA macros, or if you see a PDF file that's got JavaScript running on it. These are fairly common attacks, and it's something I've been working on a fair bit since I had a customer get just a lot of Dridex, a lot of it. We actually saw that this Cridex rat was being embedded in Office documents with the Visual Basic exploit there, like, hey, open this, and then it installs the remote access Trojan, allowing a whole lot of access into your systems. So taking a look at that code, we see a lot of commonalities. Mainly, if you've ever used like the Metasploit framework to generate an attack, you can see that one of the ways they get around common detection is to randomize that code. And let me show you what that looks like. So here I have a PDF document generated by Metasploit. So if you open this in the right version of Metasploit, it actually initiates a call home. And if you're running Listener, you get a prompt, right? Well, let's take a look at what some of that stuff looks like. And for that, I'm going to use ClamAV, which, I mean, let's not kid ourselves, all AV sucks. But in the effort to be a good AV, Clam does a lot to normalize a document. So it will unpack executables, it will normalize code, it will extract objects from PDFs, which is sort of what I'm doing here. So if we take a look at that, I'll run Clam, it's going to parse through this PDF. Yeah, it's going to check all the AV signatures, and actually it's going to come back with a hit. There's a heuristic score that actually says, hey, there's a lot of weird hidden stuff in this. But it's also extracting all the objects that make up a PDF document, so I can take a look at them individually. Now if I take a look, now I have a directory here, and change it into that, you'll see I've got 4 files. These are objects that were pulled out of the PDF document. We can see that 2 of them are empty, which is fairly typical, because if you're just generating commodity malware, you generally don't even put anything in the PDF. There's no text in it, right? There's not a lot going on there. But you'll see another object in there coming through as ASCII text. And if we take a look at that, it does not look like ASCII, right? This is looking like hex. So let's put that back through a hex dump in reverse, and we get our code. So here is JavaScript code. right? Those of you that know, if you don't know JavaScript, you're looking at this and saying, this is looking weird as hell, right? If you know JavaScript, you're looking at this and saying, this looks weird as hell. And that's kind of the point, right? Because what we're trying to do to get around AV, to get around an IPS or anything doing a static signature, what we're doing is randomizing that code. So it's essentially like an en masse for and replace on your code. Take your variables and replace them with random nonsense. So if you take a look, you'll see, okay, here's a variable name. Right? Here's a variable name. It's random nonsense. I've written some very awful code in my days. Completely illegible, no comments. On my worst day, it's never been anything like this, right? This is randomized on purpose. And that's something we can look for, right? If I can't look for something else, can I look for someone trying really hard to hide from me? Can I look for an absurd amount of random stuff in a file and find that? Right? Okay, so that's where information theory comes in. So it's actually a branch of mathematics put together to look at how do we quantify and measure information, and by doing that we can actually get to a point where we can measure the amount of randomness going on in a file. Alright, so information theory is actually started by this guy. His name is Claude Shannon. He wrote a paper called The Mathematical Theory of Communication, which is just legendary in the field. Started the idea of looking at communication as a digital process. And by doing that we can actually look then at sort of measuring the value of information and how much information is included in a message, right? And I know that sounds weird. I'm going to go a little more explanation there. So, turns out, if you want to seek the value of information, what it really comes down to is how much surprise does that information give you, right? I know it sounds a little counterintuitive, but think of it this way. If you had a machine that every hour on the hour spit out the number 1, and you waited around, okay, it spit out the number 1. You waited around an hour. You know it's done this a million times before. Every hour on the hour spits out the number 1. You wait around, and an hour from now, it spits out the number 1. What have you learned? Nothing, right? So we'd actually say that that process is an entropy of 0. There is no information coming out of the screen because there's no surprise. There has to be an element of surprise for us to really learn anything, and that's what information is. So we can actually look at measuring that. Now, you've probably heard the term entropy before. That's what we actually do to measure the amount of information in a message. You've probably heard in the terms, physicists use it though, where entropy measures the uncertainty about a physical system, where the physical system exists in one state of many states. To an information theorist, uncertainty is about the message. But at an integral level, it's essentially the same thing. Instead of being the state of a physical system, we're looking at, out of all the possible messages data could be, why is it this one? Right? And at its core level, the entropy between information, the entropy in physics, is exactly the same. Right? So we're just talking about measuring two different things. Physicists are looking at measuring order, and information theorists looking at measuring information, which, once you drill into it enough, turns out to be the exact same thing. Like literally at a quantum level, the exact same thing. So these are literally, at a mathematical level, information theory and physics meet and describe the same things. So we're looking at measure of surprise. And to boil it down, so when I start talking about measuring entropy, a good way to think about it, and I think that's the best one to sort of hold as a framework, is the average number of yes-no questions needed to guess what's in a message, right? So if someone's like, okay, I'm going to flip a coin, it's either heads or tails, how many yes or no questions is it going to take you to guess that one, right? 1. Right? Because and that actually translates to 1 bit of entropy, right? So a coin is capable of holding 1 bit of information. Here's how we copy it, which isn't that important to the discussion, but I want to throw it up there because if you happen to remember the formula from your physics class, it's the exact same one, right? And I'll say it's fairly easy to calculate. We're looking at the negative sum of all the probability of any given possible message times the log of that possibility. And we add it up. And a logarithm can happen with any base. You'll normally see it in 10, in E, or 2. 2 is by far the most popular, especially anyone remotely tied to computers. In the original paper I mentioned earlier by Claude Shannon, he would call this the binary digit, which he shortened to bit. And that's where the term was first seen in print, right? So this really is affecting a great deal of things that come since then. And by the way, when we get down and talking about that at a physics level, I've pulled the image here that they did in Interstellar. Yes. If you haven't seen the story, they actually hired physicists. They took racks and racks of computers to generate a model of what does a black hole look like, because no one knew, right? You never visited one. So they actually had to run these simulations. Okay, what does light look like when it's around a black hole? So we know what it would look like on a movie screen. No one had ever thought about it before. They ran a simulation, and physicists were like, oh yeah, of course it looks like this, right? No one ever thought of it before, but now we know, and of course it's gorgeous in the movie and on the screen here, but I want to mention that because, again, tying those things back together, the debate now is whether or not black holes destroy information, right? Because the entropy is actually the same at a quantum level. That's a current paradox in physics, although apparently I don't understand it. But last week, a physicist out of OSU actually presented a paper where he said that if you sucked into a black hole, you wouldn't be destroyed. When you hit the singularity, when you touch the surface of singularity, your body would be destroyed, and you would be instantly turned into a hologram of your former self. I don't understand that at all. But apparently, it resolves Einstein's paradox of what actually happens at the center of a black hole. That's all I understood about it. Okay, so take a coin flip, which I actually went over before. I came to the conclusion that it's one bit of information, but to go through the mathematical formula, it has two states, heads or tails. Probability of being each is 0.5, right, or 1/2. So if we take 1/2 times the logarithm of 1/2, which is -1, add those up, we get one bit of information, right? And of course, you already knew that. We know what a bit is. A coin holds one bit of information, but we can apply that to anything. So if we were to start to look at, say, the alphabet, or if someone's typing out a message, now we have 27 different things, like, letters in the space, or however many you can include in a message, right? So instead of looking at heads or tails, it would be A, B, C, D, all of them, right? And now we can start to measure that. And in fact, once you measure it, Shannon actually sort of estimated that 50% of the English language is redundant, right? So that I would ask, right, can you read this? And oftentimes we can. When things are missing from a message, we can still read it because there's redundancy in the language. So we could say that English language is 50% efficient, and of course there's engineers in the crowd like, we got to fix the English language. You don't want to. It's redundancy in messages that allow for error correction. And a mathematical layer, that's exactly what happens when you see communication protocols talk about a parity bit or doing a checksum. If you include some redundancy, you can check to see, did my message get screwed up? Right? So it's essentially the same thing as saying, okay, can you read this? Right? Because there's enough redundancy built in, we can still understand the message. So, how do we apply this to analyzing malware? I'm talking really fast. It was an hour talk originally. I've got half an hour. I'm sorry for that. I will take any and all questions when this is done. Until then, I'm talking fast. Sorry about that. Let's take a look at some malware. So what I did was collect some malware samples from Cisco's threat intelligence platform. So it'll pull out and say, okay, show me all the malicious documents we've collected. I pulled out in my original sample 1,024 documents. I'm now rewriting the code to do it again with 10,000 samples. Initial results look the same as what I've got here, but that's the next step. So we did that. I extracted all the VBA code I could from those documents. Some of them didn't have it. Some of them had some weird errors, so I got to go back there and check. But even doing that, my sample's down to 305 malware samples. So I'm able to quickly run through and run this mathematical analysis on. So what I do is take all those malicious documents, extract the Visual Basic code, and now calculate the entropy of that code, right? Because now if someone's gone and randomized that code, we should have a much higher entropy score than regular code. So in Python, really not that hard. Once I've got my files, all I have to do is open them up. There are great libraries for managing and pulling out the Visual Basic code and things that are in a Word document file, right? So as long as you can import these functions here, the OLI tools, OLI VBA, that function, so just download that, use the function here, pass it, your file into the VBA parser, extract your VBA code, and now I pass that through the Shannon entropy function, which we can also import, right? So if you've used Python before, pip install these functions. These are the few lines of code you really need to measure that, right? The code is slightly more complicated to do this all at once, collect all the data, because we wanted all of these statistics in a single array so we could compare them to others. But that's essentially what it took to run through this math. So what happens when I actually did this? Well, when we looked at the entropy of malicious code, came back with a mean score of 5.28, and standard deviation 0.25 about, right? So what does that mean? So let's lay down some frameworks, right? Is 5.28, is that high, is that low? What the hell's going on here, right? Well, first let's compare that to English. We talked about how it was 50% redundant. If you look at, we got roughly 27 letters. It's about 5 bits of entropy. But if you measure how language is actually used, it comes out to about 2.6, and that's why we get that 50% redundancy. 5.6 is compared to 5. So 2.6 is English. So we know there's a lot more entropy than normal English language. But is that a huge surprise, right? I mean, code isn't the same as English, right? So we may need a different framework. And to sort of box it in, the theoretical limit to entropy is 8, right? Completely random noise should have an entropy of 8, but even when you measure data in the real world, what you're talking about is like a high 7. You don't really see 8. It sort of approaches 8, right? But if you get to where you're measuring this kinds of code, or you're looking at binaries and what's in them, and you see an entropy score higher than 7, that's encrypted stuff. No question about it. It's completely random or it's encrypted, which is at an entropic level the same thing. All right, now to give it a better comparison though, instead of looking at the English language, how about looking at other code, right? So what I've done is collected all of the VBA macros that were on the Cisco security share drive, pulled those out, and then like every Python script I had on my machine, right? So I read those in, calculated the entropy of that, and what we have is a very different score. That had a mean of 4.75. Which ended up being significantly lower than the 5.28. And by significantly, I don't mean I'm saying that. I mean I ran a statistical test to test the hypothesis that these two number series were the same, or had the same mean, rather. And that was rejected with confidence far greater than 99%. So statistically speaking, there is a significant difference in the entropy score of the malicious code we've observed, because it's so common for people to randomize that code to get around AV. Right? Now, here's those data points plotted out. It's the same data on the left and the right. They're just plotted differently. Here it's just plotted on one dimension. So here, from the bottom moving up, we have a higher entropy score. And then there's a marker for every document I observed with that entropy score. So here's in one dimension. We can see, it's mostly around here. The edge is sort of cut off, but here at the bottom, we're an entropy score of about 4.6. Here at the top is about 6. You can see the mean being about 5.2 right around here. On the right-hand side, it's the same data points but spread out. The horizontal axis doesn't actually have a meaning. It's the number of observations. So that's not data, but I wanted to spread out the data so we get a different view of it, which has turned out to be actually really useful. I'm now looking at a lot of this data to find the outliers and to find clusters. Because take a look at that. There's a line going right across that graph, right? If these are all random processes, we shouldn't observe this kind of pattern. So what it looks like is a lot of the samples of malware I've collected have the exact same entropy score. So what we can also do with this data is start turning around and using it in our attribution algorithms, right? So again, one of the next steps is start comparing. All those that have a similar entropy score, are they calling home to the same IP addresses? Are they built similarly? Are they loading the same DLLs, right? Are they about the same file size? And start to tie back, okay, what it really looks like, and again, I have some more data to process in this, what it really looks like is when we find those clusters, we can say that malware is all coming from the same kit, right? The same exploit kit, the same process that generates them. Okay? So there's actually a fair bit of attribution we can do down there, as much as you can do attribution, or we can just give up on it and say what everybody else says about it. That it was shiny. Right. All right. So there's a lot of red teamers at this conference, so I want to step back and say, okay, because we understood how this worked, because we understand the theory behind it, how do we defeat the detection I've just started doing? Right? So if you're on the red teamers, if you're generating this kind of malware, if you're doing pen testing, you want to figure out, okay, how do we get beyond this kind of stuff? Because this is going to be rolling into some Cisco products here soon. How do we decode this stuff? Well, let's take a look at a message that maybe we had to decode. Can anyone not read this? because the message was screwed up and transferred, right? We're now missing a letter, but all of you can read it, right? There's a couple different reasons for that. One, there's a lot of context. The other words don't go together randomly. There's a grammar to English, so we know what we expect. And also, the letters themselves. Not all letters are created equals. And the word quiet, it's very easy to pick that out because Q and U almost always go together, right? And you ever do any code breaking by hand, or like you have a Caesar cipher, and you're trying to work that out? If you find Q or you find U, there's a real good chance you start to find the other, right? Because they're so commonly linked. So we have to look not just at letters as being random process, right? We know that all letters aren't created equal, so if a few are missing, we can generally make out what the message means. Like this one, which says, luck be in the air tonight, right? What were you guys thinking? So, here is some random nonsense, right? And this is what's called a zero-order random process, which means you pick a random number between 1 and 27, and then you select a letter that corresponds to that number. So all these letters have an equal chance of being picked out, and you look at this and you say, yep, that's some random shit, right? Just at a glance, you don't even have to read, you didn't have to count the number of letters. You didn't have to think about how the English grammar works. You look at this and you say, that's weird shit, right? We have internally processed this. And in fact, that's one of the ways they test typers. Like if you're going to type court or take minutes or something, they will type on real language, and then they'll have you type up some slightly randomized stuff to actually see how you respond. And the more English-like the language is, the faster people can go, because we have all internalized what our language looks like. So this looks weird as hell. And if you take a second, okay, there's two A's together. And then later in the same word, there's two A's together. Here's a Q with no U, right? All of this looks weird. That word is too long. There just aren't that many words that long, right? Well, instead of randomly selecting a letter, instead of saying, let's select 1 through 127, what if I said, look, some of these letters are more common than others, right? Instead of selecting a Z with the same likelihood as an E, why don't I look at the likelihood at which they're used and select them based on that? That's a first-order approximation of a random process. And we do that, and we run it through a randomizer, we get something that looks like this. So I have more vowels than we did before. And we can see that this doesn't look quite as weird. It still looks weird, right? But it doesn't look quite as weird. So I know I can do that in a first order. Well, instead of looking at how common letters are, how about I look at how common pairs of letters are? So instead of A, B, C, A, B, A, C, and all the possible two letters that can make up the language, how common are that? That gets us to a second order approximation. We start to do this, it's starting to look a bit more like the English language, right? For one thing, the word sizes are about there, right? Because we consider 26 letters and the space. And when you do that, you get word sizes that are about right. And you see here, we've got the word R. There's an actual real word in there, produced entirely by random, and there's Andy, right? And if we move past that, we can do a third order. So triplets of letters. And when we do that, we get stuff that looks like language. This is all random, but you can pronounce most of these words. None of them are actual words. But you have to read it to figure that out. You didn't get it subconsciously, immediately like the first one, because this kind of looks like the English language. And we don't have to do it with letters either. What if instead of running from 1 to 27 and picking a character, you went from 1 to the length of your dictionary file and just picked out a word? Here's a first order word randomization. How do you tell if that's random? Right. And here's a second order word approximation, where we start to weight the words by how commonly used they are in the language. And you're getting to like lorem ipsum kind of level quality here, right? You'd have to actually take a second to figure out that this is nonsense. You have to read this to determine it's all crap, but you can't determine it right away, right? And if you measure this, this is going to have the same entropy score as normal language, as opposed to randomly selecting characters, which would be all random nonsense, and we can detect by calculating the entropy. And of course, I've done this for the English language, which might be a flaw, right? If you're writing code in another language, you're going to have a whole different set of probabilities. So, is my stuff horribly biased? Potentially. Well, let's talk about the malware, because I'm running out of time. So taking a look at the malware, we can start to ask, okay, well, are malware authors concerned about this? And, of course, because I have an English language bias and there's a whole lot of malware being written by people who aren't native English speakers, how might they get around that? Let's take a look at the data again. But here we take a look at the bottom, because now that we've got a process that catches most commodity malware here in the middle, we want to take a look at the outliers. What's going on with those? Why are those super random? And, of course, at the bottom here, why is this stuff that I know are malicious, right? I extracted it from my malware database. Here's stuff that I know is malicious that they're having an entropy score way, way closer to completely normal code. Why is that happening? So I took a couple samples and looked at them. Example 1 had an entropy score of 4.74, which is right in with all the other good code we saw before. This is not standing out as malicious by calculating the entropy. But there's a whole lot of other stuff going on in there. Okay? So we take a look at this, and this is a bit blown up here. I looked at some of the functions that are included in that code, and we can see here that included in the malicious code are these functions like add customer, which runs through and pulls data from the spreadsheet and has pop-up buttons. And then there's a few other ones. There's function for edit customer. So again, it's building some sort of database, and now you can edit it. There are functions in here, and they're commented. Right? There's a comment for these code. So there it is kind of blown up. There's a comment for this code here, which is show all customers, right? So now it looks like we have a fairly regular database kind of thing happening in Excel here. Well, the thing is, if you take a step back and you actually look at how the code executes and how it's called, what we do is have code that's processing names and phone numbers from an Excel sheet that will never run. This code is never called. There's no data in the Excel sheet. There's no way that code is initially executed. While that code is in there, it will never actually run. And if you get past that, you start to see, okay, this is included for absolutely no reason except to make the mal code look less malicious. And once you drill past that, you get to the real functions. Here's what they're trying to do. Here's the actual malicious code. And it's the same kind of crap where they've encoded their real code, and then they're decoding it, right? So what you do is you take your code, translate each letter to ASCII, and then pass it back to the character function, and that's what it's doing here. So you see all this randomized nonsense. And to get beyond that, there was something, I thought this was really cool. They don't call this code either. So if you're doing full static analysis about what code runs, you miss it because it does not explicitly call this code. It does not explicitly call the function. What it does here at the bottom, check it out. On error, go to this function they set up. That's where the malicious code starts. And then it calculates, let's do a little math for no reason. Let's calculate A equals 129 divided by 0. Isn't that great? They actually set up their malware as the error handling routine and then cause an error. That's fantastic. That's one of those cool moments where you're getting through malware and you're like, oh, that's so smart, right? There's so many times you stop and think, like, I'd really like to have a beer with whoever wrote this and figure out what they're thinking, right? So, kudos to them. And I actually broke it out by module because a lot of Visual Basic code will be broken out into different files. And calculated the entropy that way, and it was no help. Right? The malicious code is totally embedded with that, and in fact, if you look by entropy score, the highest scores had no malicious code in it. That module had the highest entropy. There is malcode in 3 and in 5 here, and they had totally normal scores. Someone is putting fake code in with the malicious code just to make it look more normal. How do we catch that? Well, we saw that it's trying to open a file. If all that code executes is trying to open a file, we saw those functions. We saw an obscene number of those character functions. We see that it's trying to run code from a DLL. We saw a lot of base 64 strings. And we can do like a static signature. You can do like a clamsig or a yarasig because this has been seen before. This was not a unique sample. Thank you to everyone who puts their stuff on pastebin. That's the only reason I knew this. Because I could go and search for the same kind of crap out there. The padded code, the edit customer, and show all customers, all that crap, they're reusing that. The malicious code is randomized every time. Every time. But they are reusing the padding fluff code. And again, only know that because I was able to Google it and pastebin popped up, which is fantastic. All right. How about another example? What transcends language? It does, right? But if you're writing code, you might not be able to do it in math. So what words transcend language? God damn it. Yeah, all right. But we're in code, we're writing code, that's the foundation, right? Anything?
Music, picture, beer, porn. Bread, apple, grapes, very small rocks.
From now on, all questions are hypothetical. Take a look at this code. All of the randomized variable names are first names. So the guys writing this malware are not randomly generating words. They've got a list of first names, and they are randomly picking from that. Whenever they randomly generate their malware, they substitute in first names. All right, so now we have this function Haywood, which takes the variable Ronaldo, and then maybe that'll call this function here Gaston, which is going to take the variables Gaylord and Manuel. All right. Here's some more of that. That might not be totally random because there are definitely some non-English, there's some, I'm going to say Spanish because I don't know shit about other languages, but roughly Spanish or Latin of some sort, right? Santiago and some of these, right? So maybe there's a tie back there to a place in the world or where this is coming from, but holy crap, how are you going to catch this stuff, right? Of course, some of these names are rare enough that I'm not looking for them. So if I parse Visual Basic code and I see Domingo and Ronaldo in there, I'm actually flagging that to review later, right? Otherwise, they got me, right? I'm patting myself on the back over here like I use math to detect malware. I'm a fucking genius. And as soon as I do that, I'm able to parse through the code and find the people who have already outsmarted me. All right? Which is not to say this is without value. I'm still knocking out all the commodity stuff. You generate something in Metasploit and send it my way, I'm going to flag it because I've already pulled out the code, calculated entropy, and I see you're doing some shitty randomization. Now I know about it. All right? And then after that runs, we actually see it call home. It downloads malware from here. There's the URL. There's the IP address. This is like a week and a half old malware, so hopefully your stuff, like this is already on your blacklist. But it's there if you want to check. Also, the user agent. The user agent on this thing, you won't believe me unless I show you. Let's look at the HTTP. Here's it is calling home. Follow TCP string. There's the user agent. So it calls home to a web server, and it doesn't say, I'm an Internet Explorer, like every other web browser, and just fake it. No, it randomizes every damn thing. So this calls home, it says, yeah, I'm a web browser named Arnoldo. Because it's just, it's like, hey, I've got my names, I'm getting past all your entropy shit. So we can do that, right? So maybe keep looking for non-standard user agent strings, right? Because if you pick up Arnoldo here, and I have actually seen the user agent string Arnoldo in a few different samples. I'm not sure that's quite as random as the rest of the code. All right? So something to look for. So we keep going. And that's life of being on a blue team, right? It's a little different. If you're on a red team and you're just trying to get in, all you need is a nice stash of ways to get in. But when we start looking at ways to detect malware, we know there's a shelf life. We know that if we have a great way to detect malware, it's only a matter of time before they figure out another way around it, because malware and the ways to detect it are constantly co-evolving. But we want to be aware of that process. That doesn't mean this is now crap, the malware people got around it. It means now be part of our toolbox. We can use these kinds of functions and knock out all the commodity stuff. And you take a look at that graph I had before. If I knock out, do I have the, I should have put another copy there. This one, right? If I knock out all the shit in the middle there, don't you have a lot more time to focus on the weird stuff? Don't you have now the opportunity to find the outliers, which are left now are the more advanced attacks anyway? And that's the value of this stuff. Maybe someone gets around it eventually, but for now, I think it's a pretty cool way to start to process this stuff. And of course, now that we have some sort of metric, we can knock out everything in the middle and start focusing on the outliers, which at the end of the day is the best you can hope for on a blue team. because there's not enough time in the day, and there's a whole lot of malware out there, so we knock out the easy stuff, and you have a chance to find the outliers. You know, we've got a chance to really find the people targeting you and the people that are succeeding and getting in and getting out, right? So let me, stupid build. All right. Yes, okay, there, yeah, all right, thank you. Again, I think we have to start moving out of here, but once we get everything moved, any other questions you have, I'll be around for a while, please feel free to ask them, and I apologize for having to race through that.
Yeah, if you guys could maybe grab a couple of chairs and help stack over here.